Okay, let's have a look at this graph. I need to open up, make a beautiful graph. Okay, let's have a look. Right, so just one question? Yes, just one. Okay, so graph this, use your graph. Okay, add an extra row. Potential difference and current. Right, so first question. What goes on the X and what goes on the Y? So what goes on the X? Current. And here? Voltage. Yes? Yeah. So on the X is current. So let me put the current in first. So current. And what units? Is it amps or milliamps? Let me see. I did give you amps. How nice of me. Current. Current in amps. Okay, the first one? 0.5. 0.7. Is it increasing like this each time?
Yeah.
0.25 increase. Okay. Until. Okay, and the voltage, the potential difference in volts. Firstly, 1.75. 1.625. 1.5. 375. 25. 125. Okay, 1. 0.875. 0.625. 75, of course. And 0.625. Right. So, question 1. Probably make a beautiful graph. Graph. Okay, let's make the graph. Okay. Scatter. We'll do it like this. Your graph was decreasing?
Yeah.
Okay, whatever. Question 1. And the graph title, we'll call it I against V. I in amps and the Y, V, potential difference in volts. Your graph looks like this? Yeah?
Yeah.
Okay, and I should put in a line. So let me draw the line. So beautiful. I just need to make it a bit smaller. Okay. Good? Yep. Do you get something like this? Yeah. Next. Where's my questions gone? Use your graph to get the internal resistance. Okay, so do you remember on the graph which represents the internal resistance? The slope or the intercept? The slope. And what's the slope here? Or what did you get? Mine's a half. So what's the internal resistance? 0.5. A half. Yeah. Easy. What do I want next? EMF?
Yes.
So EMF, problem, Grace?
No.
You sure? Okay. Next is the EMF. What's the EMF on the graph?
The voltage?
Yeah. What number on the graph? In the graph, it is the intercept. It's where the graph crosses the y-axis. So where does your graph cross the y-axis?
2.
It crosses it at 2. So the EMF is 2. Next.
As a row of resistance.
Resistance. Okay. So now we'll have a row for the resistance in ohms.
Wait, what is the unit for EMF?
Have a guess.
Newton.
Newton? Oh no, way off. Unit for EMF? Volt. Yeah. Next is calculate the resistance, isn't it? Right, so if you think about your triangle VI OR, what does OR equal?
Resistance.
Which equals?
Resistance.
Yeah, no, the formula.
Oh,
V over I.
equals to I.
Yeah, so here we have V over I. Okay, what do I ask you to do next?
Add an extra row of load power.
Power.
P equals to
P does equal something, indeed. Now, I might have to just go to my drawing pad here for a second. Okay, so I think it would be helpful if we just quickly draw this experiment. So what you have is here, the resistance which you can change. This is called the load. And then up here, you remember you have your battery, your cell, and what's beside it? A small internal resistance, like this. And here we have an ammeter, and then here we would have a voltmeter. So when you use the formula or equals I over V, which I were you using? You were using this I. And which V were you using? You were using this V here. So that means this or is the resistance here. Yeah. So if you want the power equals IV. But you can I want to put this, well no, I could just leave it as IV. So power is IV. So that would equal I multiplied by V. So here's the power. Okay, what's next? Great, okay. So I just delete this graph. So what I want to do now is I want to make a graph, and on this axis is the resistance here, and on this axis here is the power which comes out from the resistance. So if this was a light bulb, it's the power of the light, or whatever. Okay, so let's make the graph. We'll do it, oh yeah, looks nice. Load power against load resistance. The x-axis is resistance in ohms, and the y-axis is power in watts. Now this is actually a very interesting graph, because what this graph tells, it's actually a famous graph in physics, and what this graph tells you, if you make the resistance too big, you get less power. And of course, if you make the resistance too small, you get less power. There is a resistance that you can use that will give you the most power. So what exactly does this mean? So if we think about like, oh, you didn't see my new phone.
Oh, you changed your phone?
Oh yeah, look.
Look here.
It's slightly better than my old phone.
Oh.
Yeah. Actually, they don't make this anymore. I had to buy it second hand on eBay.
How much?
What do you think?
How many €10?
You're close, actually. 25.
Oh, it's expensive.
Oh, for me, it's quite expensive. Yes, quite expensive. Anyways, what I was saying here is the battery has internal resistance, and in this example, the load would be the phone. Okay, so if the phone is really a powerful smartphone, the resistance will be really big. then that means the phone has less power. But also if the phone was a really small, cheap phone, then you would have less power. There is a place where you get the most power for your resistance. And the answer is when the resistance is 0.5. Now that 0.5 should sound familiar. Where do we see 0.5 in this question? Yes, that is right. So this leads us to a very, very interesting and important result. Here, if you want the most power, then the external load resistance, you should make it equal to the internal cell resistance. This gives you the most power for your device. Yes. Interesting. What this means is, if your battery is bigger and has a bigger internal resistance, then you can have a bigger external load. Yeah. And actually this in physics is called, I think it's called load matching, where you match the load to the internal resistance. Have you ever seen this before? No. It's important for electronics. Is anyone doing electronics next year? Ah, you are. Yeah. Just you? Yeah. So you will see this result again. It's an important electronic result, the load matching. Okay, next lesson? No. Not yet, okay. By the way, I saw this question in the exam. Like, this is the type of question you could get in the exam. So usually the graphs are nice straight lines, but sometimes the graphs have a hill shape and you want to find the top. Yeah?
No.
Not yet, shortly. Green tea? Green tea?
Chinese tea.
Yeah, green tea.
Not green tea.
Black tea?
No.
Not green tea, not black tea.
Because green tea, many color looks like green tea.
So what?
They have different names, individual names.
Ah, individual name.
Yeah.
It's called?
Shampoo.
Oh, terrible tea. Terrible. Terrible. Okay, got this? Okay, next lesson, so.